All right, today's Wednesday, April 10th. With the weather and the flooding, I had the class leave early. So this session here is for everybody, the online students and the students who were in the class. And on account of that, I thought we'd skip ahead a little bit to page 240 and 241 and look at pulleys. This is a nice kind of self-contained unit we can go over online pretty easily given the situation, I think. So that's what we'll do. Right, so pulleys are used a lot in industry. They allow us to lift things to gain mechanical advantage, and they're used a fair amount, so we want to be able to analyze them. So in industry, sometimes they call this rigging when you're in a mill. It's different ways of rigging these pulleys to move things around. So this covers 2 pages. The first page kind of covers the basic idea of how to analyze these pulley systems, and then derives how to solve the problems. That's page 240. Page 241 has actually a quicker method to solve the problems, but I think it's useful to go through page 240 first because it kind of makes 241 easier to understand. Okay, so what we have here is a 3-pulley system, and we're going to pull down on the rope at D at 0.4 meters per second, and we're going to do that for 1.5 seconds. And what we'd like to know is how high does this weight move? How much does it move up, and what's its velocity? Okay, when I've got a system like this, the first thing I want to identify is how many ropes are actually being used here. So I just track the ropes around, like so. So really all I've got here is one rope wrapping around all 3 pulleys. It starts right there, and then it works its way around. So what I'm going to do here is I'm going to start with the pulleys in this position, and then I'll finish with the pulleys in the position down at the bottom of the page. Now, what I'd have you notice here is that there are some constants here, things that don't change regardless of what position the pulley is in. Okay, what I'm going to do here is I'm going to start from a fixed point that doesn't move. And that's going to be up here, the line of A and C. That's not going to change anytime during the problem. And I'm going to measure from that down to the moving points, down to the center of B here, and down to the end of the rope at D. Now, when I'm in this position here where I start, and the position at the bottom of the page when I finish, I have some constants here that don't change. I've got the distance from the end of the rope to point B. That doesn't change. I've got the distance around that pulley A that doesn't change. The distance around pulley B that doesn't change. And then the distance around pulley C that doesn't change. Okay, so regardless of which position I'm in, I've got those constants that I just marked there. Okay, so right there, and right there. Now, the reason I'm calling these out is they make my dimensioning dB and D sub D a little bit more complicated. So I'm going to kind of call these constants out as separate so I can isolate them from my equation. And I think that might make a little bit more sense when we work through this. But what I'm doing, I'm going to call these constants here. This one's C1. When I go around A and C, I'll call that C2. And then when I go around the big pulley at B, I'll call that C3. Okay, so they're constant distances. Now, the method here that I'll use is going to be to find expressions that are based on those dimensions, D sub D and D sub B. And I'm going to come up with an expression for the full length of the rope that starts where I marked there just a minute ago, right here, and then goes around the pulley system and ends up over here at the arrowhead. All right, so what I'm going to do, I'm going to use the dimensions D sub B and D sub D to do that. So if I start at the end of that rope over here and I work my way up, well, that's d sub b minus, which is that full distance from A to B, minus C1. Okay, so there's the beginning length of the rope. Then I'm going to wrap around pulley A. That's a distance of C2. Then I'll come down from the level of A to the level of B. That's D sub B. Then I'll wrap around the big pulley. That's C3. Then I'll go up another distance of D sub B. That takes me from the level of B up to the level of C. Then I'll wrap around pulley C, which is a value of C2, and then I'll drop from point C down to the level of D, and that's D sub D. So that's an expression for the length of the rope. I can add it up and collect terms. I'm going to have 3 dBs, 1 D sub D, and then this collection of constants, minus C1 plus 2C2 plus C3. All right, so that's the length of the rope. Now what I'm going to do next is pull for 0.4 meters per second over 1.5 seconds. So this point here, D, was up here, it's moved now. 0.4 times 1.5, 0.6 meters down. And that's going to change the configuration of the pulleys a little bit. Now A and C aren't going to move, but B is going to move up, as will the weight. And then the rope will move down. So what's going to happen then is the distance from the level of C down to the end of the rope is going to increase by 0.6. And the distance from A and C down to B will decrease by some unknown value that I want to find. That's delta B, which is how high the weight is lifted. So now I can do the same thing I did before. I can come up with an expression for the length of the rope. But instead of using D sub B and D sub D, I'll use D sub B minus delta B over here and D sub D plus 0.6 over here. All right. So I'll go from A to B. That's my D sub B minus delta B. But then I have to take away C1 right there. Okay. Then I'll go around pulley A. That's C2. So I'll add that in. Then I'll come down from the level of A to the level of B. That's dB minus delta B. Then I'll go around the big pulley. That's C3. Looks like I forgot to mark that earlier. Okay, then I'll come back up from B up to the level of A and C. That's D sub B minus delta B again. Then I'll go around the little pulley here. That's C2. And then I'll come down a distance of D sub D plus 0.6. Okay, so I'll collect terms. I get 3 D sub B minus 3 delta B now, plus a D sub D plus 0.6, plus that same collection of constants. And that's the length of the rope. So what I have now are 2 expressions for the length of the same rope. So what I can do now is equate those 2 expressions together because the length of the rope hasn't changed. It's the same in both positions. So the expression that I generated the first time through is over here on the left, and the expression I just generated goes on the right. And I can cancel things out. Okay, the collection of constants are the same on both sides, so they just cancel out. 3D sub B cancels out, and D sub D cancels out. So everything cancels out on the left, so that's 0. And that'll equal minus 3 delta B plus 0.6. So what I can do then is set 3 delta B equal to 0.6 and solve for delta B. That's 0.2 meters. That's the change in height over the 1.5 second time period. So I can take the 0.2 and divide it by 1.5, and I'll get 0.133 meters per second, which is the velocity. Okay, so that's the basic idea of how you can figure out the relative motions, you might say, or the motions of the pulleys, depending on when you start pulling on the end of the rope and what's going to happen. So if you pull down on that rope at 0.4 meters per second right here, pulley B, which is attached to the weight, will go up at a third of that, 0.133 meters per second. Okay? That's what's going to happen. I will mention that that's one rope and there's 3 points of contact. It's not a coincidence here that if you pull down with 0.4, you come up at a third of the velocity of 0.4. That there's a connection there, okay? Now let's look at a little quicker way to do this. So this is method number 2 on the next page. And what we're going to do is use the method we used on page 1, but we're going to simplify it a little bit. And I'll find a quicker way to apply it. So what I've got is the velocity of D is a given. It's 0.4 meters per second. And I can use that expression I generated on page 240 on the top to get the length of the rope. It's right here. 3 dB plus d sub d plus that collection of constants. Now you'll notice that the constants canceled out on page 240, and that's commonly what happens. So for that reason, when you do this, a lot of times you don't even bother with the constants. You just put in the variables. The variables are these dimensions that you measure from your datum, your set point that doesn't move, down to the points that do move. Okay. So what we have then is the length is 3 dB plus d sub d. Now what you can do with that is just take a time derivative of it. The time derivative of distance is velocity, and the derivative of a constant distance is 0. So when you take the derivative of L, that just goes to 0. The derivative of 3 dB becomes 3 VB, and the distance and the derivative of 3 d sub d becomes v sub d. Okay, so you just come up with an expression for the length of the rope. You can omit the constants, and then just equate that. Just come up with your basic L equals, whatever that happens to be equation. Take a time derivative. The time derivative of the length goes to 0. On the right-hand side of the equation, those distances turn into velocities. Okay, so what we've got then, when we solve that, is minus 3 VB equals V sub D. V sub D is 0.4. So solving for VB, we get negative 0.133 meters per second. So what's happening there with that negative is we're measuring down. So that negative then means that the velocity of B is actually up. Okay. So that's the method. Why don't you see if you can apply the method on page 241? There's a problem there. Let's see if we can figure this out. If we pull this cable at 2.4 meters per second to the left, what will happen to the velocity of D? What's it going to do? Or what will it be? Okay, and I've got a little hint here. Dimension from a set datum to the moving parts. Remember to do that. The dimensions can extend vertically or horizontally. So why don't you pause the recording and see if you can find the velocity of pulley C, which would also be the velocity of D. All right, so hopefully you paused and worked through that. Let's have a look at the solution to this. Okay, so what I want to do here is I want to dimension from these set points to the points that move. So I could, now what you choose for your datum, you could do it slightly differently than I did it. It's not that big of a deal. The important thing here is that you dimension from a point that doesn't move. That's the important thing. So when we do this, I just dimension down from the ceiling here because it doesn't move down to C. So that's S sub C. And I dimension from this pulley to A because the B doesn't move, the pulley won't, and A will. Now I could have dimensioned this dimension. I could have started it at E. I could have started this dimension at B. I'd still get the same result. So, you know, you don't have to do it exactly the way I'm showing it, as long as you have the right concept there, okay? So given what I'm seeing there, I can write up an expression for the length of the rope. Okay, and basically I'm going to have two of these SC dimensions because the rope goes down and then back up. Now you might think of that as being a constant and the wrap of the pulley as being a constant, so they can be ignored. And then I've got SA that I add in. So the length of the rope is 2 times my distance to C plus 1 times the distance to A, and that equals the length of the rope. I can take a time derivative then, and I get 2VC plus VA is 0. So VA is minus 2VC. VA is 2.4. So negative 2VC is 2.4, so VC is negative 1.2 meters per second. Okay, so that negative means the velocity acts in the opposite direction as the dimension. So I'm dimensioning down to get to C, so the negative means C is moving up. All right, so that's the basic method there. And why don't I give you one homework problem here that'll be due on Monday. So how about 161? And we'll have that due Monday. Okay. All right, there we go. So we'll call it good.